Well, good evening, everyone. My name is Brian Hoskins, and I'm Director of the Grantham Institute here at Imperial College. And it's my pleasure to welcome you to our annual lecture in 2013. And it is then a great pleasure to welcome our speaker, Thomas Stocker. He's Professor of Climate and Environmental Sciences at the University of Bern. He's been very involved in the Intergovernmental Panel on Climate Change since 1997, in the third and fourth assessment reports of the physical science basis on climate change. He was a convening lead author in both of those. And then in the fifth assessment report, the one that was launched in September, he was actually the co-chair of that. And he was extremely busy through the last 3 years up to then, and certainly since then. It's fantastic that he's been able to find time in this very busy period to come and see us. For those who saw the streaming of the actual summary for policymakers and the press conference that took place then, he had not been to sleep for at least 30 hours. And if you saw him answering questions from the Daily Mail at that time, then he did a remarkable job. But he has recovered from those 30 hours, and he's continued on. But to give a little bit of history, he was actually, his PhD was in mathematics, in waves on water, in shelf waves. And after his PhD in ETH Zurich, he moved to London, to University College London for a year in the mathematics department there. And he moved on to other postdocs then in McGill and Columbia, and moved towards longer timescales and more towards the climate system and the thermohaline circulation and centennial variations in the atmosphere-ocean climate system. And that's what his expertise has been in that ever since then, in climate dynamics and paleoclimate modeling and the reconstruction of paleoclimates. So it's a great pleasure for me then to ask Thomas Stocker to present the 2013 Grantham Annual Lecture. Thomas.
Thank you very much, Brian, for this kind introduction and invitation to come back to London, actually after only a brief pause, because I had the privilege already just a week after this exhaustive experience to introduce the report here to the community of the Royal Society and beyond. So thank you very much, ladies and gentlemen. It's a great privilege to be here. What I don't want to do tonight is to just inform you what is in our report, in the fifth assessment report of the Intergovernmental Panel on Climate Change. I should say it's only the first of 3 parts that has been published, the part of the physical science basis. Now, by now, I presume these major messages are out there, so I will spend only a short time of the allocated 45 minutes on that one, but then move quickly to a topic that I personally feel is of equal importance, and that is the question about climate targets. Basically, what options do we have for the future, given the declared will of the governments of the world to limit climate change? In multiple documents this has been declared, and the question therefore to the physical science is, do we have a realistic chance to actually meet that challenge? So, as I alluded to already, I will divide this presentation into three parts. I'll talk briefly about the Anthropocene, which is a new epoch in our history of change on this planet. I will then go briefly to the fifth assessment report and then spend most of the time regarding climate targets. Anthropocene was introduced, I believe, for the first time in this clarity and in this context by Paul Crutzen and Eugen Sturmer in basically a newsletter by a then global research program, the International Geosphere Biosphere Program, IGBP, basically indicating to the public that we are living in a time where mankind is leaving a permanent trace on this planet. How can that be? How do we define the Anthropocene? Well, if you talk to a geologist and you ask the person, what is the Holocene, or what is the Pleistocene, or what is the Miocene, they always refer back to a paleoclimatic record from the sea sediments, from the ice cores, or from another archive that they have analyzed. And they give you a time period that they can identify by having performed certain measurements. And that's exactly the same idea of the Anthropocene, that in 100 years or 1,000 years' time, the then climate scientists will take ice cores from Antarctica, that will still be there, analyze these ice cores, and even if they do it with no technological advance, even if they do it with the analytical tools that we have developed so far, they will see a trace of the carbon dioxide concentrations that we measure today. In other words, they will be able to identify this period of time where man has left an imprint, and they can perform many analyses. They can perform trace metal analyses in sea sediments. They can look at ice cores. They can look at tree rings, and they will realize that this is a distinct epoch. That's behind this new term, Anthropocene. So we are living in the Anthropocene, and obviously, because this is a new epoch, we look at indicators that are unprecedented in the sense that they show values that we haven't seen for a long time. For example, this curve here, the carbon dioxide concentrations reconstructed from Antarctic ice cores over the past 800,000 years show to us natural fluctuations that are in pace with the ice age cycles. There were 8 roughly ice age cycles over the past 800,000 years. And I've attached to this curve the observations of the past 60 years, direct measurements from Mauna Loa and many other stations of carbon dioxide concentrations in the atmosphere. And we realize here that 2013 was actually the first year during which, at some period, the concentration of carbon dioxide exceeded 400 parts per million. Now, if you compare that to the concentrations that we measure over the past 800,000 years, then we can make the statement, a statement of fact, that today's concentrations are 30% higher than ever during the past 800,000 years. This is an unprecedented fact, an unprecedented observation of a measurement in the atmosphere. The chemical composition of the atmosphere was changed by the emission of greenhouse gases caused by the burning of fossil fuels and deforestation, and a little fraction through cement production. If you look at a shorter time scale, and here I show you the emissions of greenhouse gases as reported and collected by the International Energy Agency, also these emissions are unprecedented in human history. They've increased from about 5.5 gigatons of carbon per year to almost 10 gigatons per carbon per year in the year 2012. We're today at 9.7, unprecedented, and an interesting observation is that since the legendary Rio conference in 1992, this emission has increased by 57%. Why am I referring to Rio 1992? Because arguably this is a time point where you can say confidently that the world has known about the problems. The policymakers have known about the problems. Otherwise, they wouldn't have convened this conference. And yet, the emissions have increased by 57%, writing every year almost a record emission value. You see around 2009, the effect of the financial crisis and the actual very quick recovery with respect to fossil fuel emissions. Let me now come to what is in this report, the report that was launched on September 27, 2013, after a huge effort of the scientific community. It's important to remind ourselves what the task of IPCC is, this Intergovernmental Panel on Climate Change that was founded in 1988. And in our procedures, it's written that our task is to assess on a comprehensive, objective, open and transparent basis the scientific information relevant to understanding scientific basis of risk of human-induced climate change. There are a few more words that also look at impact and socio-economic implications of climate change. These are dealt with the other two working groups, Working Group 2 and 3 of the IPCC. Now, in the course of these 25 years, 5 assessment reports have been produced, and the latest one, the most recent one, is now out, that of Working Group 1, and any information you can actually take from this dedicated website, including data once it's released, mid of January, that provide you with atlases of regional climate change projections and all the chapters that are available on that website. Now, in order to give you a little bit more background information, basically to appreciate the vastness of effort that went into such an assessment, I want to briefly reflect on the process. Because I believe whenever in the past IPCC has come under criticism, the public wasn't really informed well about the process that is behind it. In particular, about the possibility for the wider public to actually look at the reports in their draft forms and provide comments. Of course, you need to have a little bit of expertise, and I will explain in a minute what that means. In 2009, scientists, government representatives, and other stakeholders have come together to approve the outline of the 3 working group contributions that are to be published in the year 2013 and 2014. It's important that the governments were involved right at the start to basically send the scientists off with a clear charge. For Working Group 1, that meant that the governments and also the scientists, of course, wanted to have more information about, for example, sea level rise, a topic that was, I should say, not in the full depth assessed in AR4, in the 4th assessment report. Another topic that was also the focus of this recent report is the topic of clouds and aerosols and their interactions. And so in the approved outline, we saw in 2009 a chapter of clouds and aerosols, as well as a dedicated chapter on sea level change. Once this outline, the chapter structure, was approved, we also knew what kind of expertise from the scientific community we required to comprehensively cover this assessment. We could therefore select authors from over 1,000 nominations that were received by IPCC, of scientists and colleagues who volunteered or who were nominated by their governments to contribute to this assessment. The 259 authors operated in various functions. There were authors who coordinated entire chapters, other authors who were lead authors of a chapter. Typically, a chapter has about 12 to up to 17 lead authors, led by 2 to 3 coordinating lead authors. But there were also review editors selected right at the outset of the report to ensure that the review process was following according to the procedures. In this review process that I have mentioned already, it's called a so-called expert review process. We wanted to make sure that we have the widest possible coverage of experts. So our drafts were put on the World Wide Web, protected with a password, and the password could be obtained by enlisting yourself as an expert. Now you can imagine that it's hard for us to decide who is an expert and who is not an expert on climate science or specific issues and topics within climate science. It's hard to distinguish between a person who maybe has published 100 papers and another person who has published 5 but very influential papers. So what we did was to basically put the burden onto those who enlisted to review and asked them to explain to us in a sentence or two why they believe they are experts. Tick a box and then you had access to the report. So basically it's as wide as possible that this review was organized. We had 2 rounds of this review, one for the first order draft, a second one for the second order draft, and an additional round of government review on the summary for policymakers. In total, we've received 54,677 review comments. And anybody of you who has ever published a scientific paper, you perhaps get reviews back from 3 reviewers with a total perhaps of 25 comments. And personally, I can tell you, having read 25 comments usually on my papers, I have enough work to do for the next 2 weeks. Now here we received 54,000 review comments, and all of them were considered by the authors of the 14 chapters and had to be responded, either taking action in revising the chapter or explaining why this particular comment was not pertinent or some other action was taken. So really a thorough poll of the scientific and expert community on the emerging report. The report itself consists of 14 chapters, ranging from thoroughly looking at the observations, a few chapters on the scientific understanding of climate processes, and then a few chapters on the projection of climate change. In total, we have more than 1 million words in this report and over 1,200 new scientific diagrams that accompany the text and illustrate it. A new innovation is this atlas of regional climate projections, an atlas that is derived from the 2 million gigabytes of numerical data that has been obtained through a concerted effort of climate model simulations. Out of that, we look at 35 regions over the world, and these data, basically temperature and precipitation change information, is available for the public free of charge and for analysis. Obviously, nobody would read 1 million words from cover to cover, let alone those who take decisions on our behalf, the policymakers. That's why we also write a summary for policymakers. Basically a highly distilled product out of the million words into 14,000 words. But still, our experience from the fourth assessment report, which was published in 2007, suggested that it is a tough task for a non-scientist to read a summary for policymakers, which is full of numbers, ranges, uncertainties, likelihoods, and also has scientific diagrams. That's why for the first time we try to even more condense our messages, and we therefore have proposed, and it's now approved, 19 headline statements that are essentially the key messages from the summary for policymakers in short, quotable words. They all print on less than 2 pages. So I can truly say there is no more excuse for a very busy person not to have read and understood our messages. And I may also say that many media have actually simply quoted these headline statements. This told us that we were on the right track. It was language that is understood by a wide public, by readership of newspapers as well. So I already mentioned 3 topics. What has changed? Measurements, assessment of the changes in the atmosphere, in the ocean, in the cryosphere, on the land surface. Then a group of results and assessments regarding the understanding. How does the carbon cycle respond to the changes of carbon in the atmosphere, but also to the changes in temperature and precipitation, for example? How do the clouds respond under changing concentrations of aerosols, for example? Or what is the climate sensitivity of the Earth system? And then a large body of chapters and material regarding the future of the climate system in response to emission scenarios. Note that here an additional element of uncertainty comes into play, and that is the uncertainty of the choice of the emission scenario. It's a non-scientific uncertainty. It's something that the natural science cannot resolve. It's basically us who decide which emissions will take place in the future. One of the statements from the observations is this one. Warming of the climate system is unequivocal, and it goes on to explain why that is so. This is a statement that we have repeated from the fourth assessment report, and we wanted to make sure that we do repeat this statement, which is a powerful one, already present in 2007. And we now have more information from the climate system to actually make a stronger statement that starts with the same opening, also indicating a historical timeline of these assessments. A second simple statement is human influence on the climate system is clear. And that is a sentence that is in the summary for policymakers, and you may wonder why the governments actually agreed to that with not much resistance or intervention. The reason is that all the scientific information with all the numbers, the caveats, the uncertainties, and the entire assessment is available in the respective section of the summary for policymakers. And this is just the headline conclusion of trying to summarize simply, succinctly, and quotable what the assessment of the scientists is. And another example from these headline statements is the following. Limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. This is a typical sentence that you may hear from a scientist giving an interview or an NGO person giving an interview. Now, this is a sentence that IPCC has formulated in consequence and in light of the underlying scientific assessment. This sentence has gone through review multiple times. The governments have commented on it. It has been discussed in Stockholm at the approval plenary, and that is the result of that sentence. Not only do the scientists agree with this sentence, but also the 194 governments that make up IPCC. Now, this is the climate system as scientists depict it. Very complicated, many processes, many components, many scales over many orders of magnitudes, both in space and time. An extremely complicated system. And I often hear the question, how on earth can you make precise projections or relatively precise projections of such a complex system if you're not even able to predict the coming 15 years in temperature? Now, the reason why we are confident providing projections to the policymakers are some fundamental physical characteristics of the conservation of mass, energy, and other quantities in this climate system, which looks very complex, as you can appreciate. But in essence, what we want to know is if we have anthropogenic carbon dioxide emissions, all we want to know is what is the change in global mean temperature in response to these CO2 emissions. Of course, we want to know much more, but this is one of the fundamental questions. It's a question of climate sensitivity. You probably have heard about this, and here something is missing. Maybe not, in terms of this one here, climate sensitivity, but there are other quantities here that actually provide a much more policy relevant information, and I want to focus on this one. Now, from emissions to temperature change, I mentioned climate sensitivity would be the metric. But if you take a different view, and instead of trying to relate concentrations of carbon dioxide in the atmosphere to temperature, if instead you look at the cumulative emissions of carbon dioxide from the early industrial epoch, say from 1870 to 2011, and put that into relation of the warming that has happened since then, you find out that there is quite a powerful relationship between these two quantities. Just as numbers, during that time period, 515 gigatons of carbon have been emitted in total, and that has led to a warming of 0.85 degrees Celsius. I should also say I'm giving here a very simplified view of not only the climate system, but also the drivers of the climate system. Because there is a whole menu of drivers. It's not only carbon dioxide, but carbon dioxide stands out because it's the strongest driver and is the most permanent driver in the climate system. If you look at the cycles of carbon, you realize that the carbon dioxide molecule is staying for a very, very long time in the atmosphere and acts on the radiative balance. Now, the quantity that links these two numbers, the cumulative emissions and the warming, is called transient climate response to cumulative carbon emissions, TCRE. And if you've been preoccupied with climate sensitivity up to now, and media in the running up to the release of the Working Group 1 report have made sure, some media have made sure that people are preoccupied with climate sensitivity, and this is an important metric, but this metric here is as important as climate sensitivity. And it has a policy relevance, as you can appreciate, because it makes a link between what man has emitted in terms of carbon dioxide through the combustion of fossil fuel and the effect, the response that the climate system provides and influences then the changes in all other components of that system. Now, this relationship between cumulative carbon emissions and warming has been tested in coupled climate models of the most advanced stage available to the scientists working in the fifth assessment report. These simulations were carried out by over 20 climate modeling centers. Over 40 models were available. A smaller number also included carbon cycle processes. But the message that you get out of these models is clear. You see it in these two diagrams. On the left, you see experiments of an academic type in which the carbon dioxide concentration in the atmosphere was increased by 1% per year. The cumulative carbon emissions were then back calculated by looking at the changes of carbon in all the inventories of this model and plotted against the warming that you see on the y-axis. And you see these models all show a fairly linear behavior between cumulative emissions and the warming, with a slope that is in fact this TCRE, this transient climate response. And you see there is an uncertainty associated with this slope. A similar picture emerges from simulations that are using the so-called representative concentration path scenarios. These are emission scenarios that were developed by the scientific community to be used by climate models, making projections based on different assumptions regarding the future development of the world, ranging from a world in which strong policy intervention would result in a reduction of greenhouse gas emissions, and a world where essentially emissions evolve according to business as usual. These simulations as well show that there is a really linear relationship between cumulative carbon emissions and the warming. So you see, this is a pretty robust finding from coupled climate carbon cycle models. And it's actually an astounding finding in the complexity not only of the dynamics of the atmosphere, the responses of the clouds, the warming, the changes in precipitation, but also the response of the ocean to the increase in carbon dioxide concentrations, the uptake of carbon into the ocean, but also into the land biosphere, that there is this simple linear relationship. And therefore we say in the summary for policymakers, cumulative emissions of carbon dioxide and global mean surface temperature response are approximately linearly related, and that linear relationship is measured by TCRE, which is estimated at 0.8 to 2.5 degrees Celsius per 1,000 gigatons of carbon. Just to put that number, 1,000 gigatons of carbon, into context, and you will see this number later on again, you've seen already the number, actually. About 10 gigatons of carbon per year are emitted by human activity. Now, this is the last figure in the summary for policymakers, and I can tell you we have deliberated many hours with the governments over this figure, how to precisely formulate whether or not to have that figure. But I report with satisfaction that we have not lost a figure. This is a fundamental figure for the summary for policymakers. It shows you in the black curve, starting from the left lower corner, the historical evolution of cumulative anthropogenic emissions and temperatures as simulated by these climate models. In color, you then see the 4 emission scenarios, with the lowest one in dark blue that goes up to just about 1,000 gigatons at the year 2100, with a warming that is short of 2 degrees Celsius. Whereas the other scenarios go a longer path on essentially the same line. The largest emission scenario, the business as usual scenario, emits a lot of carbon, and therefore cumulative carbon emissions increase quickly in the course of the next 100 years, up to the year 2100, with a total of almost over 2,000 gigatons by the end of the 21st century, and a resulting warming of 4.5 degrees Celsius. The policy relevance of this graph is actually given by the fact that you can read off any temperature warming that you choose to consider and determine from this graph the emissions that are cumulatively compatible with that warming. For example, 2 degrees, more than 1,000 you cannot emit. And if you look a little bit more closely to this graph, also considering other greenhouse gases that are also emitted by human activity, for example, methane through agricultural processes, or nitrous oxide, then this cumulative emission has to be read off directly from the scenarios that include these additional greenhouse gases, and that results in compatible emissions of less than 1,000 gigatons, only about 800 gigatons of carbon. Now, put that into context of the emissions that we have put into the atmosphere up to now, 515 gigatons, and you realize we have already used up more than half of the compatible emissions with a 2-degree target. That and a much more general interpretation of this diagram leads us to make the statement in the summary for policymakers that limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. Now, what does that mean? I show you in this table the 4 emission scenarios and the assessment of the likelihood to exceed the 2 temperature targets that are defined in the documents of the UN Framework Convention on Climate Change. The 1.5 degree Celsius target is likely to be exceeded by all emission scenarios, but the lowest one. The 2-degree target is likely to be exceeded by the 2 larger emission scenario, one being the business as usual, the 8.5, and one a high stabilization scenario, RCP 6.0. For the second lowest emission scenario, there is actually a sizable chance that we also exceed the 2-degree target. We say more likely than not, which means more than 50%. So many models are compatible with the 2-degree, but a majority of the models is not. So you see, there's essentially only one scenario that provides us with a possibility to stay below 2 degrees, and that is RCP 2.6. The question now to scientists who look at technological feasibility of a specific scenario, these are not the physicists that have produced our Working Group 1 report, but these will be the colleagues in Working Group 3 who will look very carefully at the requirements of each specific scenario. Let me now come to the last topic regarding climate targets. A burning question: what can we actually achieve? And I look at the emissions and realize that actually a good approximation to these emissions is an exponential increase at a rate of about 1.8% per year. And for back-of-the-envelope calculations, that's actually sufficient. I then go on to present a few academic emission scenarios. This is really an academic exercise that should inform us about some fundamental limitations to achieving climate targets. A scenario that essentially shows an exponential increase until a specific time in the future, for example 2020, and then an exponential decrease, reduction in emissions from there on. And I now can use the concept of cumulative emissions, which is nothing else than the area under this curve, to relate that to the chosen target. I take here a scenario that is compatible with the 2-degree target, and the prediction from this academic scenario is that from 2020 onwards you have to reduce by over 3% per year your emissions. If you instead decide to wait a decade and have to peak in emissions only in 2030, in order to achieve the same amount of cumulative emissions, you have to go down at a steeper rate, 5.8% per year. And you can continue this exercise. Another decade tells you that you have to reduce by almost 20% from 2040 onwards. And you can see where I'm heading at. There is a natural limit here, and that is as soon as the area under this increasing branch of the emissions is completed at the 1,000 gigatons that are compatible with the 2-degree, you essentially are about to lose your 2-degree target. And we can depict this very simply in a few formulas. Cumulative emission is just a time integral. The warming is proportional to cumulative emissions, and that proportionality is this TCRE, transient climate response to cumulative emissions of carbon. And what it turns out, if you calculate, if you assume this academic scenario, is that your peak temperature is a function of your decision when you peak your emissions and the rate that you are able to reduce your emissions. That's a very simple story here. And you can actually show the simple story in a diagram. You see on the horizontal the starting year of the emission reductions. You see on the vertical the climate target that you envisage. And the graph gives you the reduction that is required. For example, if we take a rate of reduction at 2% per year, then you see that weighting actually increases exponentially the target that you're able to achieve. But you can also read this graph in a different way. You can ask yourself, where is the infinite reduction rate? Infinity is where the red line is. And that implies that when you are on this red line, you have bought some waiting time, but from then on, you have to basically have zero carbon dioxide emissions. In other words, this graph shows you the growing area of unachievable climate targets. So if you have 2 degrees and you accept this academic scenario, you hit the wall at 2042. If you say, okay, I'm an economist, I know that I cannot switch off emissions from today to tomorrow, but I may actually be able to sustain a reduction of 5%. That's what you find in the economic literature. Then, of course, you have to start earlier, and your emissions peak somewhere between 2025 and 2030. If you'd like to give more time to the economy, a smoother ride towards a carbon poor economy, then of course you have to start earlier. Take, for example, 3%. And you see, we're actually now in the same decade that we are living now. It's about 2018 that you have to peak your global emissions if you say we can muster 3% reduction sustainably starting from 2018. I want to close with another consideration that actually is also embedded in this very simple example. We go back to the peak warming. Delta T is proportional to cumulative emissions. And we ask ourselves, how does delta T depend on the waiting time? The waiting time for peaking global emissions. So we take the time derivative of this. We assume that TCRE is a characteristic of the coupled physical carbon cycle climate system, and therefore you take only the derivative of the cumulative emissions, which depend on the time when you start your reductions and on your reduction rate. And it turns out that there is actually a very simple relationship between what we call the mitigation delay sensitivity of the climate system, the time derivative of peak warming, and the peak warming itself. It's simply connected by the rate of emission increase between now and the time of peaking emissions. You can now work out in numbers how big that sensitivity is, and it's quite instructive to look at this relationship. It suggests an exponential relationship between for this peak temperature. Peak temperature, peak warming rises at the rate of emissions, and we can actually show that in a graph where you see again time on the horizontal, the emissions on the vertical, the observed emissions up to the year 2012, here with these diamonds, and then basically an assumption of 2.4% per year reduction at various peaking times with the indication of the peak warming that you get. And as you wait, this warming goes up. We can even work out the rate by comparing that rate to the rate of the observed warming. For example, in the 20th century, we observe a rate of warming of 0.08 degrees Celsius per decade. In the latter part of the 20th century and the past 12 years, 0.12 degrees Celsius per decade. The warming pause, some people call it, 0.05 degrees Celsius per decade. This one here, the increase of peak warming is much faster, 0.4 degrees Celsius per decade. So a decade of negotiations and waiting for implementation of emissions reduction costs you about 0.5 degree Celsius of your climate target. Now that is, I believe, a very policy relevant statement. Committed peak warming rises by a factor of 3 to 8 faster than the observed warming. Let me close with showing you the world according to these climate models for the lowest emission scenario and the highest one. RCP 2.6, equivalent CO2 concentration by the end of the 21st century, 475 ppm. This is temperature change relative to the end of the 20th century and below precipitation change. The world is warming. Precipitation changes are hard to actually see. There is a lot of area that is showing this hash pattern, which indicates that the model simulations show changes in precipitation that are not distinct from the natural variability in the climate system today. But they are there, the changes are there. In the business as usual scenario, the world looks quite different. The colors are more intense, indicating larger warming. A world that has a global mean warming of over 4 degrees Celsius, with enhanced warming over the continents and over the high northern latitudes, with a warming there exceeding 7 degrees Celsius in the annual mean. But what is really concerning is the fact that also precipitation now shows large changes. You see areas where there is significantly more precipitation, 40 to 50% more precipitation in certain areas of the tropics and the high latitudes of the northern hemisphere. But more disturbing areas where we have reductions in these model simulations of precipitation by 20 to 30%, for example, in the Mediterranean area and the subtropical areas. Both areas that already today are challenged by water shortage. So to me, this is really a signal that we not only have to look at the warming, which by itself is a challenge through its implication of changing extreme events and sea level rise, etc., but it's the primary resource of humankind and ecosystems, water, that will change substantially in these high emission scenarios. Let me summarize. These are the three most important headline statements out of Working Group 1, Contribution to AR5. And from these considerations that I've shown in the second part, these climate targets actually disappear rapidly as carbon dioxide emissions continue. We need to be honest to ourselves. A 2-degree target may be an option today, but in a few years, it won't be an option any longer. Committed peak warming increases at rates similar to those of the emission increase, 3 to 8 times faster than the observed warming. This is also important because some policymakers actually say, shouldn't we gauge our emission contributions or emission reductions contributions on the international level based on the observed temperature change? In other words, if you have a phase of not much temperature change due to natural variability, would say, oh, we can relax a little bit. This would be a fundamental error in your decision making, because we know that there is this committed warming that increases at the pace of the increase of emissions. And finally, we do have a choice to try hard and ambitiously and forcefully to aim for a world that is less than 2 degrees warmer than pre-industrial, or continue to realize that we are on the course of continuing losing climate targets, losing options, and then having to cope with life in a world that is 4 degrees or more warmer than today. Thank you very much for your kind attention.
Well, thank you very much, Thomas. And now we're in the session for a few questions. So if you would like to lift up your hands. Right, I can see one there. And if we have another microphone, you might get it over to there for a second question.
Thank you very much for the presentation. I think you're probably far too polite to say this, but is it your view that last week and the previous week's exercise in Warsaw is really just an exercise in cognitive dissonance? Because at no point during the 2 weeks of the negotiations was there any discussion whatsoever about incorporating the 2 degree Celsius budget into any of the decisions that were adopted.
Looking at the pace of these negotiations on a more historical time axis, it would be asking too much to see a document coming out of Warsaw that already firmly puts the finger on the cumulative emission or the budget approach that we have shown here in our summary for policymakers. What I can say is that some of these headline statements that you see here were actually taken verbatim in the opening paragraphs of some of the documents, in particular the document of the ad hoc working group on the Durban platform. And for me, this is actually one sliver of hope that the scientific message has arrived. It has not yet arrived in full swing where it really makes a difference, and that is with the carbon budget. But the policymakers are aware of it, and I may also say that in Warsaw, the scientists were given quite a sufficient amount of time to directly explain the science to the policymakers, and that is a hope that I carry. We'll see how that plays out for next year then in Lima, and then what is really the litmus test is COP21 in Paris, where the policymakers have to come up with a new agreement, because that is the time that they have set to themselves.
Right, so there's one over there who has the microphone.
Good evening. Thank you very much for the presentation. Very interesting. With regards to the emerging nations and their development and innovation in technology, in science and engineering, do you think they will be a major stumbling block to any future climate change protocols you may try to implement or influence? With regards to China, India, Brazil, etc.
I mean, these countries that are, you know, in full swing of development, they are hard partners in the discussions. And I personally have some sympathy for that. But eventually, what is clear also to those countries, if you accept the scientific insight and assessment of a limited budget that goes along with any definition of a climate target, then it's very clear to everybody that every country eventually needs to fit into this budget somehow, at the common but differentiated responsibility that is also engraved in these documents of the Framework Convention. But it's clear, at some stage, all the countries have to join the effort. And hope is in technology, I fully agree.
The next one's over there, and then it's down here.
Thank you for a wonderfully clear distillation of what's an incredibly complex topic of the science of climate change. I just wondered when you were going through to the end with your climate budgets and the time at which we effectively run out of the opportunity to keep below 2 degrees or some other target. At that point, you started to neglect the uncertainty in all of this. You were very clear early on that the TCRE is probably somewhere between 0.8 and 2.5 degrees, about a factor of 3 uncertainty. But when we came through to the budgets, you were obviously just assuming one single value for the TCRE. I wonder if you could tell us what the value is. And also, do you think that that then leads you into some possible danger that people who don't like the particular value that you've chosen can say, oh, well, it could actually be lower than this. Look at the pause we've seen for a few years, and then we don't have to act quite as fast as you think we do.
Absolutely. When Brian invited me here for this lecture, I told him I don't want to just present the IPCC assessment. So I'm here as much as a co-chair of Working Group 1 as a scientist also. And what you saw in the 2/3 of this lecture is basically a flavor of what science can provide in addition. And I can assure you any of these numbers that I said in this lecture, none of these numbers is in the report. The report is really taking very seriously a reporting of best estimates where we can give them, plus the ranges of uncertainty. So we would never quote a specific year in the report. This is for illustrative purposes. Of course, you could then carry out the exercise with the highest and the lowest of the range of TCRE, and you would get a corresponding range of these years where your climate target expires. But then come the economic scientists who tell me, perhaps by the end of the 21st century we will have new technology in our scenario and we can remove a lot of carbon dioxide from the atmosphere. Have you considered that? Obviously, we have not gone into these details. This is really a very simple back-of-the-envelope calculation to bring the message basically to the public to say, look, waiting has some implications on your options, something that is actually common sense. I've never seen anybody multiplying options by simply waiting. It simply doesn't work.
Rainer Mayer, Institute of Education, University of Reading. I'd like to add another layer to your discussion, and I refer you back to the limits to growth scenario in the 1970s by Meadows and others, where the jury was asked whether the world would run out of resources or die of pollution. And I would refer you to the following fact, that all the models of peak oil indicate that once the world's oil supplies peak, that the rate of decline of oil each year, every year, for at least the next 50 years, will be 3% a year. So if you took the diagrams you showed, if you looked and added in the extra peak oil would suggest we have to stabilize by 2017 because we'll be forced economically to make do with less oil.
That may well be the case, but peak oil is also a highly contentious topic where there is not a lot of agreement in the circles of the geologists. Some people say it's there, other people say it's perhaps there in the next 10 years, others say we have already passed it long ago. I'm not sure whether we can trust or hope for peak oil then to magically solve the problem and provide us with this 3% per year reduction magically once we've noticed peak oil.
Perhaps we can move on to another. Why don't you ask at reception? Okay, it is. Right, so in the front here.
Jay Mather. I was recently at the All-Party Parliamentary Panel on Climate Change, and what was really interesting there was the absence of the Energy Minister, the Climate Change Minister, the Treasury, anybody really. There was only a handful of MPs who even showed up for the IPCC briefing. Another very interesting point was that a few years ago, with the threat of a pandemic, the government spent £1.2 billion on a 1% chance that there was going to be a pandemic. We're sitting with a 95 plus, and we're not even spending that much. The cognitive dissonance, which was mentioned before, we're in a situation where evidence is making no difference in human behavior. We're not evidence-based creatures. We're just simply not. We're proving it. So it's interesting, the fourth version, the fifth version, the sixth version. Is this going to make any difference? Isn't it time to become unreasonable?
It's a justified question, absolutely, but I'm resisting the temptation to give up, because it's the task of the scientists to provide the best possible information that we can give. It's the task and responsibility of the citizen to draw conclusions from what is now very simplified and understandable messages by going to elections, vote, exercise your democratic rights if you think that's the way to go. So, and, you know, whenever you can link a problem, even with the slightest probability, to a health issue, it makes all the difference. Ozone hole is another one, where people really accelerated, apart from the fact that there was also a replacement product at the time. Shouldn't forget that. We don't have a replacement product that produces a gas that has no radiative forcing.
You're up there then. Okay, push it. Up there.
Yes. My company develops and files patents relating to battery improvement use for electric vehicles. And we obviously believe that we can turn the graph down rather than watch it going up. The problem that we have as we see battery-powered electric cars hopefully replacing fossil fuel cars is that it's incredibly impossible to find information relating to the mining of metals for the shells and the components within that battery, and also electric charging over those batteries and how they can be developed using non-polluting systems. I would really like to ask you, sir, if you could assist us on where we can find that information to help bring that graph down.
Well, that's a tough call to a climate physicist. I think you are here in an excellent environment of brilliant engineers at Imperial College, where I'm sure that along with other engineering schools, some people have actually started looking into that issue, into that problem, and also I think there's a...
I would love their names.
Send us
Brian?
an email. Send us an email.
Okay.
Right, and this is probably the last one there, President.
Yeah, this is another question possibly about reasonableness and unreasonableness. But the targets whatever they are, need ultimately to be translated into something that a very large number of different countries have to sign up to, and of course that's what we're seeing being played out again and again. There was, about 10, 15 years ago, a very promising idea, contraction and convergence, system by which you could actually mathematically set out a series of charts which actually then placed responsibility on different countries to contract and converge at different rates. Does that theory, in your view, still have validity?
I must admit that I'm not aware of that theory. Has it to do with the historical carbon footprint or the cumulative carbon footprint of a specific nation?
Just taking the emissions from where they are now and all.
Oh, the
converging
wedge,
on
the
a certain
7
level.
wedges? That
Well,
one?
no, converging onto a certain level by, say, 2050 or something.
Well, I mean, whatever target...
Per capita.
Yeah, per capita.
Yeah.
Whatever target you agree as a global community, be it 2 degrees, be it 3 degrees, or 1.5, implies within the uncertainty a cumulative budget. And now the next task, which is much harder, is to allocate that remaining budget. Most of it we have already emitted into the atmosphere, but allocating that remaining budget, and some of the discussions in Warsaw actually have already started with interventions by, for example, Brazil, to request from the scientists an account of the historical cumulative emissions per nation. Now, as a physicist, I can say it's actually difficult to look at the map in 1750 and identify nations that are still around. Switzerland is, the UK is, but many other nations aren't. So it starts already there, the historical development of the notion nation. I think it's not a very helpful one, although the political decisions are nation-based, but ultimately it comes to the per capita use of carbon or emissions of carbon dioxide. That's ultimately where we have to get at. And you mentioned that the UK has this goal of reaching per capita of about 2 tons per
2
capita
tons per
by
person, which would be equivalent to that.
2050. You know, these are things that the industrialized countries have to think about if we're serious about the climate targets.
Okay, at this point, I think we'll hand over to Professor Maggie Dolman to give a vote of thanks. Please stay around.
So I have to say this is always a very challenging spot in the evening, not least because I know that I am the only thing standing between you and the reception. It's also particularly challenging when I can only consider myself, at best, an intelligent amateur on the topic, as I am tonight. However, on this occasion, it has been less of a challenge, and in fact a joy, because of the precision and the clarity of your presentation. Even the maths didn't lose me. Now, I definitely didn't read the million words, I have to confess, of the recently published Working Group 1 report, but I did dip into the summary, actually, and the headline statements. And again, I think the clarity of presentation was quite extraordinary, without any patronising oversimplification. And in that report, and what we've heard tonight is certainly sobering. There's no doubt about that, and it's clear that time runs out for action unless the engineers can come in and save the day. Thank you all for attending this evening, and you are all welcome to join us at the reception. But most importantly, finally, Thomas, thank you very much for this beautiful and edifying presentation, which has stimulated and will continue to stimulate a fantastic discussion. Thank you very much.
Thank you very much.
Thank you.
Thank you. Thank you very much.
So clear.